되고 있는 거예요.
네. 그 상태로
Good afternoon. This is Seungeun Lee, and I'm a student of the Professor Seungeun Lee. So today I'm going to introduce what internal radiation dosimetry is in the nuclear medicine. So these are the contents. So first I will explain about what is radiation dosimetry. And second and third ones are the method for internal radiation dosimetry. The second one, the first method is organ-based, which is quite old but traditional and still used nowadays. And the second one is voxel-based method, which is quite new and still working on. So I'm going to introduce what radiation dosimetry is. So the aim is, so when you are exposed by the several radiations, such as external radiations or internal radiations, you will get the certain kind of energy deposition, and those energy depositions will cause the biological effect. So we have to quantitatively measure the radiation dose and also the potential hazardness due to biological hazards. So we are doing the radiation dosimetry. And specifically, in nuclear medicine, we say the internal radiation dosimetry because we always uptake the radiopharmaceuticals for imaging, but also the therapeutics. So especially it will be very important in therapeutics, because we have to give those to the maybe cancers or something. So we are going to talk about internal radiation dosimetry. So I just brought a figure from IAEA. So this is just a conceptual figure of internal dosimetry. So for example, if you inject iodine 131, you will be uptake in especially in the thyroid. And if there is no significant uptake in other organs, the effect will be concentrated on this area. But as you see in the technetium 99M colloid, if the source is concentrated in this liver, the organs which are near to this liver will get some radiation doses from this source. Also, but it is just certifying the just source, but all the organs can be also the source. And this one also shows all the organs can be source or target. So from now on, I'm going to explain how to calculate the radiation dose. So first, I have to define the term. The term radiation dose means the radiation energy depositions in an observer per unit mass. So we use unit as gray, which is joule per kilogram. Joule is, as you know, it is the unit of energy, and we define the dose as per unit mass. So we have to divide with the absorber's mass. And also we can use the rad frequently, but we always, I think it is the unit we are most frequently using. And so we can calculate those. And from those, we also have to calculate equivalent dose. Equivalent dose is just the dose with considering the biological damage by radiation types so radiation types. So in unit we use sievert or RAM. So what is the difference is that we use radiation weighting factor, as you see here. So what is weighting factor? You can see in this table. So as you know, X-rays and gamma rays are very penetratable radiation. So it has a quite low effect because they do not interact very frequently with the organs. However, as you see in the protons, it is particle and it has also the charge, so it has bigger weighting factor. And especially for alpha, it is very unpenetratable. So it has very huge radiation weighting factor because it always interacts with the organs very near, within the very short distance. So we have to consider these factors, and also it is also depends on the radiation energy, because if the X-ray or gamma has low energy, it will just have photoelectric absorption, but if it has high energy, it just penetrates. But for particles, if the energy is larger, it might cause the more energy deposition. So, and also it just depends on how exactly the radiation deposits in its energy in the tissue. So so we can just simply calculate the equivalent dose as multiplying the weighting factor and the dose. And then we just define some terms, and now we are going to calculate the radiation dose based on MERD method. The MERD method is, as I said, it is the fully organ-based method. So we have to calculate. There are several factors we have to know to calculate the dose. So I said the source to target organ. So it is divided by source and target, as I underlined. The first one is amount of activity and time spent by the radioactivity in the source organ. So in the source organ, there will be maybe significant uptake, and that will so number one will be the number of disintegration of the radionuclides in the source organ. Also, second one is the total amount of radiation energy emitted from the source organ. So it will reflect the energy emitted by the source organs radionuclides. So these are up to the source organs, and finally the third one becomes fraction of energy emitted from the source organ to absorbed by the target organ. So it finally reflects the interaction of source and target. So the average absorbed dose of the target organ becomes the formula like this. So let me see. This is the target organ, and this is the source organ. So the source gives energy or dose to the target organ, and these just means dose. And so as we looked at here, it will be proportional to the number of disintegrations from the source organ, and also it is proportional to the energy emission per disintegration. Also, this shows the sum of the total sum of the source to target dose. So let's see. We will see in the next slides. But so the figure here shows how the concept of this, how source organ gives dose to the target organ. But you can see here that it also target can be also source to the target. So it is just acts as a pair. And here we use just average anatomic model as just seen like this. Maybe it is from IAEA or something. Yeah, so we always use the average dose for the organ. So let's see the factors one by one. So first, we measure cumulated activity from the emission data. I mean, you can see this with the PET or SPECT images. So this is so let's see the time to activity curve here. So as the time goes, there will be biological decay and physical decay, or just biological delivery. So there will be a lot of real-time variance with the activity for all these organs. So we have to draw the time to activity curves to measure the total number of radionuclide disintegrations. As you can see, you can just count the area under the curve, as you see here. So it is called cumulated activity. So as you see here, the unit can be the becquerel with the second. So as you know, the activity is the radionuclide decay per second, and if we multiply with the second, it just becomes the number in unit. So as I said, it is the measure of total number of radioactive disintegration. So it is the dose becomes proportional to this accumulated activity, and it reflects the biological and physical decays of all the organs inside. So you can simply calculate accumulated activity as you see here. The second one is equilibrium absorbed dose constant. So if this integration occurs, it will emit some radiation, such as X-ray or gamma ray or alpha or beta, and they will have certain energies. So they are all calculated within the average value, as you see here. So this constant is defined with the every emission type, as you see here. So if you see here, it reflects the how frequent the ith emission is occurred, and energy here is just average energy of the ith emissions. So if you multiply these vectors, we can just say that this is the if you sum these values for all the ith emission type, you can say that there are some certain value of energy emissions from the certain source organ. So this if you multiply with the this constant and the cumulated activity we calculated in the in previous one. So this value becomes a radiation energy emitted by the ith emission type during the our acquisition data acquisition from the source organ. Yeah. So if you have any question, please just ask me freely. So the third one, the last factor is absorbed fraction and absorbed fraction. So this is very important one, I think. So absorbed fraction is the fraction of the energy emitted by the source organ that is absorbed by the target organ. So energy emissions from the source organ will just distributed by the nearby or far away target organs. So it is dependent on the type and energy of the emission, and also if the target is big, it will be very there will be very large absorption, or if the composition, I mean if the density or something is very huge, there will be also large dose. Also, as we define the anatomic relationship in the average human model, so it will be also reflected in here. So these are all the the function of source and target pair. So if you see the notation here, it is just the right side is the source organ and the left side is the target organ. So source organs gives to target organ to the dose with the certain emission type. And to reject the mass issues, so we can just define the specific absorbed fraction as dividing the absorbed fraction to the mass of the target target organ. So you can just define simply like this. So the total energy absorbed by the of the target from the source becomes like just simply multiplying the cumulative activity and equilibrium constant factor and the absorbed fraction. So these are energy. So if you want to calculate the dose, so I just reminded that the dose becomes energy deposited per unit mass. So the dose of the from the target H to the the source H to the target K becomes just simply dividing the target organ's mass from the total energy absorbed. So if you divide this mk, we can just simply use the specific absorbed fraction as we just calculated previously. So we use the average absorbed dose of the target as you see here. But it is very difficult to always calculate all the target and source pairs, and also all the equilibrium constants of the every emission ties for every radionuclide. It is very difficult. So there are several studies which already calculated these values, as we call it S value. So S value of the source to target is just it is just this term. This the second and third terms we calculated here. So the unit becomes the gray per becquerel and second. So it is already has been calculated. For different source and target organ pairs and for each nuclide. So we don't have to calculate this as value anymore because it is already provided from the other groups. So we can just simply calculate the dose as just multiplying the cumulative activity and the S values. So if you want to calculate the total dose of a certain target, you can just simply sum these doses from all the sources here. So this is the example of S values here. And it is from the technetium 99M. And you can see all the organs which we are taking into account and all the target organs. And you can also see that there are also the same organs here listed here. And as I said very many times, all the organs can become the source or both or either the target. And as you see here, all the organs become both source and target. And so if the source and targets are the same, they may be very large dose delivered because it is just itself. So you can see here these values, S values, are quite larger than others if the source and targets are the same along this line. And it also reflects the gamma rays emitted from the technetium 99M, and also the anatomical relationship. If the organs, source, and targets are nearby, it will give the S values will become large, but it will be very low if they are very distant from each other. So because these are already provided, you can just use it. So based on these calculations, we just define the whole body dose. But there are two different approaches, as you can see here. So the whole body dose is just simply using the total body organs. I mean, there will be just not really considering the organs or the distributions of the activities. You can just divide the total energy depositions in the body to the total mass of the body. However, it will be very inaccurate term because the non-uniformity of those distributions is not considered, and it is still questionable. So we frequently use effective dose, as you see here. So we already saw the equivalent dose from the previous slide. We take into the account of the biological hazardness with the weighting factors, as you see here, with the individual organs. So if a certain organ is very robust with the radiation, the weighting factor will be quite low because it doesn't matter. But if it is very sensitive to the radiation, it will be very high. So we sum all the targets of all the targets observed dose with multiplying the radiation factor, and we also the effective dose factors. So this is the effective dose. So there are many radiation regulations from the IAEA, or there are also like annual radiation dose we can get. It is mainly based on this calculation, but it is still based on average human model. So this is the just very simple software which is called Olinda. It is for like humans organ-based dosimetry. So I think it is the freeware. So if you put the which nuclide you used and which model, as you see here, adult or like children, and you can also put the kinetic informations of the uptakes or delivery or the biological decays, something like that. So if you just put these inputs here, the output becomes here as the dose for all the target organs with each kind of emission types. So you can use this total observed values, those values of each target organ. So you can just simply use it for the human data. So up to now we saw the MART method. So this can be the summarized method of the calculation of the radiation dose. So it is simple, but there are still limitations because it is just based on simplistic human model. So the S value is not very individualized. So we need more realistic model, but it is still under development. And also here the main assumption is that all the radionuclide uptake or energy depositions are just uniformly distributed within the organ, but it is not very true if in the reality. So this is another limitation. Yeah, also it also says that it is not very appropriate for the individualized dosimetry. So these were the MERD methods. So we can now go on to the next method, which is more complicated but quite accurate. But it is also based on the organ-based method. So you can just understand it very easily. So what is the voxel-based method? So it can be very patient specific because it uses heterogeneous anatomical or activity distribution. So you know the term voxel. The voxel means the three-dimensional tiny space. The regular grid. So you can see here there are levels of voxelizing the human anatomy. So maybe this can be the organ-based method we just saw. But if you divide these volumes to some more smaller space or to even more smaller as the head images or SPECT images, you can see the very heterogeneous distributions here. So it is also more closer to the realistic, but there are only one pair, but they are very many pairs you can see here, and it will be very much higher. So although it is realistic, but it will be very require high calculation costs. So there are several models, several methods for voxel-based dosimetry. The first one is dose point kernel, DPK. So it just measure the observed dose with the as you can assume each voxel as the source of isotropic point source, which gives dose with the as a function of radial distance. Because we are the water is the dominant proportion. It just typically based on water. And as you see here, we just multiply the cumulative activity with the kernel. And the second one is voxel-based S values. So the S values we already saw, but we defined S values with the each pair of organs. But it just in voxel-based, we can consider each voxel as an single organ. So for every voxels, we can compute those with the summing all the voxels around the target voxel. And the third one is using Monte Carlo simulations with the radiation transport. The Monte Carlo means the very probabilistic model of the radiation tracking. So it is just simply, harshly calculated with the Monte Carlo engine. And there are several types of simulation toolkits, but the very high computational environment is required because it requires very much calculations. So this is the gate. This is the most practical Monte Carlo toolkit for the dosimetry, not only dosimetry, but also imaging or therapeutics or something. So GATE is based on the GIANT4 Monte Carlo libraries, which is the Monte Carlo simulation library with the physics. And it is fully based on this GIANT4. But GIANT4 is very based on computer words. The gate we can with gate we can use very easily the GN for Monte Carlo libraries. So you can go to this website if you want to install these software. So as you see here, GATE provides the capability for those calculations of each voxels, and it also directly imports the anatomical and emission image files for voxelations. I mean, you can just use the emission data, I mean the PET or SPECT images, and also CT images for attenuations. So if you put those images, it can just simply calculate the dose of each single voxels. So this is the example using GATE for dosimetry. This is work of the Dr. Seungeun Lee from our lab, and so this is the input images of the PET and SPECT here, and if you put this, we can just obtain three-dimensional dose images. So as you see here, if there are much uptake, I mean much emission, there will be those high dose in near the high activity organs. Yeah, so the unit of the dose image will be gray, as I said. So you can use GATE for voxelized dosimetry. I mean the direct Monte Carlo dosimetry. So I just brought some examples for the publication from our group in SNU Nuclear Medicine. So this is work from Dr. Arun Gupta, and he investigated the lutetium-177 with the folic acid, and he used small animal SPECT and CT imaging. So these are the those maps he calculated by the GATE simulation. So and also if you draw the region of interest of each organ, you can define the dose for each organs, and he just calculated the dose rate in the real time. So these are the results, and also he compared with the MERS schema, which is just organ-based, and so there are quite much differences as you see here. So there were very many much differences here, especially in lungs, liver, and kidneys. And also as our group is a physics team, we also the Dr. Seungeun Lee proposed the method for more easier and simple method to calculate the dose map. So as I said here, the direct Monte Carlo, it might be the golden standard, but it takes very long time to calculate all the voxel pairs. So she mixed the voxel-based, I mean the voxel S values and the Monte Carlo simulation, as you can see here. So this the first step is the input of the accumulated, the cumulated activity, and she previously calculated the voxel S values for just simply dividing our body to air and lung and water to bone. So if you consider that if all the area is air, those uptake will be here if the source is here, and as the density becomes more higher, it will just give the dose to the nearby. So he used these kernels as you see here, and here in the step 3 we just calculate those as assuming that these are all the air areas and these are all the lung areas and water or bone, and she just drew the binary mask here, and which is really air here and really lung here and water and bone. So if you do the convolution of the those and the binary masks here, it can provide quite accurate dose map, and these are the difference between the proposed method and direct Monte Carlo method. So except the lung here, all the organs show the very small difference within the 10%. I mean 5%. And so she also used deep learning to overcome this issue, lung issue. So what is here is that if you have the PET and CT images and the dose rate map, and if you pre-train the certain unit structured the network, if so you just thoroughly update this network, and if you put the new CT and PET images here, it just calculates the new dose rate map with this network. So this is the result, and this is I think it is the PET and the CT images, and this is based on this deep convolutional neural network. So there were very significant difference in the lungs, but with those the deep learning, she could very reduce the difference very significantly here. So these were the examples of voxel-based method. So to summarize, I introduced the two types of internal dosimetry methods. So first one was organ-based, and second was voxel-based. So organ-based is quite traditional one, and so it has pros that it is very simple to use. And it is suggested by the MERD committee of the Society of Nuclear Medicine, and it is still quite used. But as I said, it is not patient-specific, and it just uses simplified phantom. And this is the huge issue, is that it assumes the uniform source distributions in all organs. So we nowadays, as the computers become to the high end, we are trying to use voxel-based method because it is for more patient-specific and realistic, which enables the individualized dosimetry or therapeutics. And it uses heterogeneous anatomy and source distributions. But it is still under verifications, depending on Monte Carlo engines you use, or like radionuclides you used, and so it is still under verification, and it is very it uses high computational cost. But I think it will be more developed, so we can be easily use voxel-based method with good computer and within the short time, computation time. So this is the end of my talk, and please ask me some questions if you have.
Monte Carlo method is practically utilized?
I think not yet, but not practically, but they're in studies. I mean, the for like studies which requires high accuracy of those maps or something, they can use the Monte Carlo method. But in like clinical or like preclinical um, equipments in our like laboratory, not yet, I think. But I heard that several companies are developing as the software which will be equipped in the scanner.
So like say if I'm performing any new therapeutic procedure in my hospital, like the TM90 sphere or
Yes.
the alpha therapy in my place. So as a clinician, I should directly go and log on to freely available Olinda and see what kind of radiation dosage we have to patient. So that is a more practical way of approaching clinical practice.
Yes, I think. But yeah. I think that it also needs more revision in Olinda still, because as you see here, there were very huge differences here. Yeah, almost like 20%. It will be very not very accurate. Yeah. Thank you for listening.
Thank you.
Thank you.